Recording in
Hello and
progress.
welcome back to our conversation about one of our colligative properties, specifically vapor pressure lowering. In our last video, we talked about Raoult's law and how an ideal solution is one that is modeled by Raoult's law, which shows a proportional decrease in the vapor pressure of solution as the amount of solvent in that solution is lowered as a result of the addition of solute. So let's see if we can't do something with this concept of vapor pressure lowering quantitatively. So let's look at an example. So in this example, let's maybe identify our goal here. So we are asked to determine the vapor pressure of an ideal solution at room temperature. So that's our goal, is to determine the vapor pressure goal. And let's ask ourselves what it is we're trying to find the vapor pressure of. So determine the vapor pressure of an ideal solution. So we are trying to figure out what's going on with the solution's overall vapor pressure as a result of us adding some component to pure solvent. So looking through this problem here, what other pieces of information can I find? So how about we start with Raoult's law? So remember Raoult's law, which is what models our vapor pressure lowering in an ideal solution, says that the vapor pressure of solution is equal to the vapor pressure of our pure solvent scaled by or multiplied by the mole fraction of solvent that's present in solution. So here is our goal, is to find the vapor pressure of solution, and Raoult's law gives us a means of doing so. So let's look at this question. Determine the vapor pressure of an ideal solution at room temperature that contains, okay, this is where we get information about our components. So this contains 99.5 grams of sucrose and 335 milliliters of water. So let's see if we can identify some information that's given to us about each of these components. So sucrose is going to be our solute. This is something that we would expect to be pretty non-volatile, right? Sugar is not something that would vaporize easily, even if it's dissolved in solution. That would not be fun for us for any of our sweetened beverages, right? If our sucrose molecules were hypervolatile. So sucrose is our solute. And what we were given about the sucrose is that we know that 99.5 grams of it were dissolved to make this solution. And I've also provided us some other information about sucrose here. I know that the molar mass of sucrose is 342.30 grams per mil. Grams per mil, but grams per mole. All right. Okay. How about our solvent? So our solvent, the more volatile substance, that is going to be our water here. So water does establish some non-zero vapor pressures at decently low temperatures. So let's see if we know anything about our water. Well, we've highlighted a quantity of water. So we have 335 milliliters of water. And I was also told the vapor pressure of pure water was 23.8 torr. So I do know the vapor pressure of my pure solvent. That is 23.8 torr. Let's look at what we have and maybe how that could be useful in our quest to determine the vapor pressure of solution. So first and foremost, do we have the vapor pressure of our pure solvent? And the answer is yes, we do. We have this. It was given in the problem, so that is not something that we need to like calculate or quantify. We'll just represent the vapor pressure of solution in torr. Why not? So we have half of what we need in order to get the vapor pressure of solution, which is the vapor pressure of the pure solvent. But now we need the mole fraction of solvent. So let's remind ourselves about mole fraction. The mole fraction of solvent in solution, in this case, would be the number of moles of water over the total moles in solution, which is the moles of our solvent and the moles of our solutes. So we need to figure out mole quantity of water and mole quantity of sucrose. So maybe let's start with our water. Because we need it in two places in this calculation. So what were we given about water? We were given its vapor pressure at room temperature, which we already used here. And we were given its volume. And I'm trying to get to moles. So the only thing that I know that connects to moles directly, like what thing relates another unit to moles, is we've got things like molarity, which is moles per liter. However, here we're talking about pure water. So we wouldn't use a concentration or a molarity to describe a pure substance because remember, a concentration is a proportion of solute per solution or solvent if we're molality. In general, we're trying to talk about like part or one component per total over the whole. So I know that I can't use molarity, pure substance. Kind of like if I hand you a glass of pure water and ask you what its concentration was, you'd be like, what do you mean? It's pure, right? So that's what I'm saying here. That's ruled out one conversion factor involving moles for solutions, liquids, whatever. Another thing that we might remind ourselves of is the utility of molar mass, which relates moles of substance to a mass of a substance. And water is a very lovely compound in the sense that, in general, at room temperature, the volume of water is equal to the mass of water because the density of water is approximately 1 gram per mil. So if you wanted to be specific, we could use the density of water as being 0.9979 grams per mil, but let's be a little lazy today. So if I have 335 milliliters of water, this means that we have 335 grams of water. And the molar mass of water, so oxygen is about 16, hydrogen is about 1. I know this one off the top of my head, that is 18.02 grams per mole. So 335 grams divided by 18.02 grams per mole gives us 18.5905 moles of water. And even then I'm carrying an extra digit here. So let's do 905 moles water. Awesome. I've got now what I need for most of my determination of mole fraction solvent. So I need this in both the numerator and the denominator. And now I need to get my moles of my sucrose. So moles of sucrose. Let's work on our sucrose mole calculation. So I've got how much sucrose? I was told that we've got 99.5 grams. And anytime we are trying to convert to a mole quantity from a mass quantity, we will utilize our molar mass. So we'll take 99.5 grams of sucrose and divide by the molar mass, which I have given to you. So that is 342.30 grams per mole. I'm checking what that is. And this gives me 0.29068 moles of sucrose. So I now have moles of sucrose, which means I need to find the mole fraction of solvent by summing those total moles. So this would give us here 18.5905 moles water over 18.5905 moles water plus 0.29068 moles of sucrose. So that plus 18.5905. Let's continue this on the next slide. I get a mole fraction of solvent equal to 18.5905 moles of water over our total moles of solution. I get 18.881 moles of solution in total. So let's take that quotient, 18.5905, 0.9840. That's the mole fraction of solvent. So now, according to Raoult's law, the vapor pressure of solution should be equal to the vapor pressure of the pure solvent before any solution is added. So that was our, what was it? 23.8 torr. Times our mole fraction of solvent. So take that product. We get 23 to 3 sig figs for torr, meaning the vapor pressure of solution is 23.4 torr. And let's ask ourselves, is this lower than the original amount of vapor pressure that our pure solvent exerts? So 23.8 versus 23.4 torr. Yeah, right? We do in fact see that this is an ideal solution. It obeyed Raoult's law in the sense that we were able to calculate or quantify and see that our vapor pressure of solution was less than the vapor pressure of our pure solvent. Now, we didn't change our vapor pressure that much because we still have predominantly water in our solution, right? We had a decent amount of water. So if we wanted to make this vapor pressure lower even further, we could use less water or add more sucrose. So this is vapor pressure lowering. In our next colligative property, we are going to be looking at something that is intrinsically related to vapor pressure, and that is the boiling point of a substance. So, in our next conversation, we'll continue this topic of colligative properties of solution by looking into boiling point elevation.